Okay, thank you. Good morning, everybody. I will present the work I did for the last year approximately. I arrived in Brest in May and doing a postdoc with Guillaume Maz and Anne-Marie Treguier. And the project is to use a neural network to predict the interior of the ocean from the surface information. And we did that in the Gulf Stream region. And it's called OceaniX-AI. So I will present you that today. Okay. The motivation is simple. We want to study the eddy scale variation of the ocean stratification. And to do that, we have profiles of temperature and salinity in the ocean, but there's not enough to resolve really this, the finer scales. But we have a satellite information that is at resolution high enough to see the eddies moving. So we want to link both. So here I plotted the mean dynamic topography, which is at a quarter-degree resolution. And here all of the profiles for 9 years of data. So that's quite a good coverage. But if I take a single day, here I have sea level anomaly for 1 day. And 1 day of profiles, there is 12 profiles that day. So to fill the gap is quite an interesting challenge. There's a lot of gaps. But we have all of this information at the surface. So the question is, can we learn a robust statistical link between the surface information and the profile so we can interpolate that in the best way? And the choices are on the profiles. We have data processing to do, because all of the profiles are not sampled at the same depth. So we are doing first an interpolation, and we made the choice to select 51 depth levels. So this is one example. There is more depth level at the surface than at the bottom, because there's more variation there and more sharp changes. We only keep the profiles that extend from 25 to 1,000 meters, and we will only predict the ocean on those depth levels. That's because so far our method does not allow not a number in the output, so we need data everywhere. So we lose quite a few profiles that are too short, and we interpolate the 25 meters to the surface when there's no data, just by extrapolating the last value up to the surface, which is quite a good assumption because it's usually in the mix layer. Okay, that's the choices we make. And then we have the period 93-2019. Now for the input data, we have the static fields of bathymetry, mean dynamic topography, longitude and latitude. And then we have the time series of so the sea surface temperature and sea level anomaly. And derivated from sea level anomaly, we are also using the surface geostrophic currents, UNV, and their anomaly. And we take the day of the year with a cosinus and a sinus of the day of the year to have it as a cycle. And we do not put the year. So the network will not know which year it is, and it cannot use this information and so we can extrapolate out of the limit, the time limit of our learning period. The network will not know that is outside of the range. That's for a better generalization. Okay. So we use a multi-layer perceptron, which is, from what I read, this is quite a basic network. And it's a simple one. We only have 2 hidden layers, and I've hidden in gray some information here, because that I will reveal later. So if we just learn temperature and salinity profiles from the surface, I'm going to show you what we get. This is the first test we did. We make classical choices by first taking 20% of our data set out for test later. And out of the rest, we take again 20% for the validation inside of the network. Okay. And then once we learn the temperature and salinity profile, we can generalize the prediction on a quarter-degree daily grid. That is the one that we see on the left, and down to 1,000 meters. Okay. But when we predicted directly the profiles like that, we had relatively good results, but I spotted two main problems on the profiles that we could solve. The first one is that near the surface, there was very often inversion of density. So we see it here. This is an observed profile in blue and the predicted one in orange. The combination of both temperature and salinity to compute the sigma zero, the potential density, shows that there is like this hook at the surface, which is the density inversion. It's not physical, it's not possible to have that on a profile. And here I show for one day a map of the amplitude of this density inversion. Almost all of the profiles have density inversion. So that's the first problem. And the second problem is that with this kind of problem in the mixed layer, we cannot compute the mixed layer depth properly. Because to compute the mixed layer depth, we use the simplest criterion, that is, we take the density at 10 meters, and then when the density is higher than this value plus 0.03 kilogram per cubic meter, then we reach the mixed layer depth. So for the observed profile here, the density is not changing until then. So the mixed layer is about 400 meters. But for the predicted one, it's going to be right at the surface because there is this problem in the density. And so this is a map of mixed layer depth for one day. We see these patches of shallow mixed layer depth everywhere because there is these issues in the profile. So we want to solve that. And what we did is two things. The first thing is that we are bootstrapping the multi-layer perceptron. So we are running it 15 times. We tested a few things, and with 15, it was good enough. And then we only take the mean of the output of all these results, and we can get the confidence interval with the standard deviation of the output also. This allows to remove some of the small variation in the mixed layer and the noise that can appear sometimes. That's the first step. And then we do a mixed layer depth adjustment that I will describe now. So this mixed layer depth, I represented it with this bubble here. And you can see that we are predicting a third profile, that is the K profile, and it's a mixed layer depth mask. So we are asking the network to give us the mixed layer depth. This mask is built like that. It's equal to 0 when we are in the mixed layer, and when we are deeper, it's equal to 1. Okay, and so the network is going to try to learn that, and for him, it can be seen as a classification problem. We are asking him, this depth level, is it above or under? And it's giving, it looks like a sigmoid function, and it can be seen as a probability to be above or under the mixed layer. So when we are at 0.5, this is the mixed layer, approximately. Okay, and then the mixed layer adjustment is going to use this prediction to correct the temperature and salinity profile, to correct the mixed layer. So let me go through one example that works very well to explain how this adjustment is working. So I picked a profile, observed profile, temperature, salinity, its density, and the MLD mask. So the mixed layer depth is about at 140 meters. And here I have two diagnostics, which are the density distribution of the error at the surface for surface temperature and sea surface temperature measured by satellites. And the same for salinity. So the error is centered on 0 for the observed, all of the data, all of the profiles. Okay, so here in blue is the direct prediction of our network. You can see that we have the confidence interval because there is a 15 prediction, and we take the mean and the standard deviation, the density, and the mask. We can see the two problems I talked about previously. The first one is the density inversion here. There is a problem. And because of that, the mixed layer depth is spotted too shallow. It's about 25 meters, while it should be around 400. The prediction is way better at the surface temperature against the SST. That's normal because we put SST as an input, so the network can predict very well an input. He understood the link very well. And SSS, it's slightly better, but not really, because we don't put SSS as an input. Okay. So now the adjustment, the idea was that one. So this mask, what we want is to reduce the gradients of temperature and salinity in the mixed layer and to not change the rest of the profile. We just want to reduce this variation. So we will just multiply by K, the predicted profile K, the gradients of T and S. On this equation, it's only for T. And the result will be this red profile. So that's what we do here. The red profile is just the gradients of T and the gradients of S multiplied by K. So above the mixed layer depth estimated, it's going to just reduce the gradients and solve this issue. So that works well. We don't have anymore the density inversion, and the mixed layer depth is located at exactly at the right location. So this example is excellent. It actually solves perfectly the problem. They don't all work that well, of course. However, another problem arises that we can see here. We created a systematic bias at the surface for temperature. So the temperature is systematically too warm. I think it's in that sense. And for salinity, we can't really see because the error between SSS and surface salinity is too large compared to what we are correcting here. So we did something slightly different, and we have an argument for that. We also spotted that the predicted profile is always showing a gradient that is too small just under the mixed layer depth. So that's another systematic bias. And so what we did is instead of multiplying by something under 1, just under the MLD, we take the mirror version of this blue profile relatively to 1. So between 0.5 and 1 for the MLD mask, so just under the MLD, we take 2 minus K. So that's what is written here, 2 minus K. And so we will multiply then our gradients by this new K profile, K star. And so what it will do, it will multiply the gradient under the MLD by something that is larger than 1 and above by something that is between 0 and 0.5. So it will reduce the gradients in the mixed layer and increase the gradient just under the mixed layer depth. And that works very well, meaning that we still solve the problem in the mixed layer and the mixed layer depth, and we do not create a bias at the surface. We see the blue adjusted with K star, the blue profiles. The error is centered again on 0. There is a small thing that we need to tune here. That is the lambda value that I said was 0.5. Actually, it's not exactly 0.5 because the distribution of mixed layer depth is not symmetrical. So it's sorry? Oh, okay. For our case here, it's 0.56 something, but we adjust that by finding the lambda that will center the best the error between SST and temperature. Okay. So now let me show you some maps of the results to see that we have a spatial coherence in the results. So this is a given day in 2018 in winter, and this is a mixed layer depth map for the prediction, direct prediction. So we see the same problem I was showing. We have patches of shallow MLD that are due to density inversions. And when we do the correction and the MLD adjustments, we have these patches that are more coherent. So we have deeper mixed layer depth just south of the Gulf Stream. There is a permanent eddies here, and we can see the jet of the Gulf Stream here is slightly shallower. And this looks quite similar with the GLORIS prediction. The GLORIS 12 is that's an ocean numerical model that is forced with all of the observations available. So it will be physically consistent and as close as possible to the observations. And it's at the 12th of a degree. That's why we have finer structures. And we compare it to Armor 3D also. That is a weekly product that is another way to use observations to do interpolation. And in Armor 3D, they have quite a lot of density inversions in this region. And the MLD definition is a bit patchy. There is some patches, but still we have a similar structure, deeper patches of MLD just south of the Gulf Stream, and this large permanent eddies kind of visible here. Okay. Another validation of our mixed layer depth map is this one. So here I'm doing an average for our time period for March and August. So that's the two extrema of the mixed layer. And I compare it with a binning of all of the profiles and Gloris mean. So yeah, the comparison for me is really good enough. The slight difference we can see is that the man permanent eddy here is displaying a deeper mixed layer depth than Gloris. Also, the North Atlantic current is slightly deeper, but otherwise we have the general shape that is very similar to observations and to the physical simulation. Okay, now enough with the mixed layer depth, and I will present you the general result because we are predicting full length profiles. And here is how it compares with Gloris and Armor 3D. So this is the two products we use to compare with. Gloris and Armor 3D are global products, and we are only focusing on one region, but still it's quite comparable. The main result is that our root mean square error between temperature and salinity, between the observed profile and the predicted profile at the same locations, we are better than Gloris everywhere, but we are worse than Armor 3D, except at the surface. So the OSNet is the orange one, and I also plotted in gray the train and test of the neural network. We see that the train and test are close, but the test is a bit farther from the profile, but still we are generalizing well. It's relatively close. Yeah, what I wanted to say here is that so Armor 3D is closest to the profile, but they do not have a very good spatial coherence, horizontal coherence with the mixed layer depth, and also they have density inversion. So here there's more data like values about this error distribution, and I want to focus on two things. The first line is the ratio of profile with density inversion is drastically reduced when we do the mixed layer depth adjustment. We come from 17 profiles with density inversions to almost zero. Armor 3D has 50%, Gloris almost zero, and on the observation dataset, we have about 1% of profiles. And for the root mean square error of mixed layer depth, we are at 50 meters with the direct prediction, and we can correct that to 40 meters with our adjustments by multiplying by the K profile, the K star profile. Okay. So just to show the general structure of our results, we have a general good coherence in our data. So here I'm showing at the surface for a day in 1993. Temperature and salinity at the surface. We have the warm jet of the Gulf Stream. We have the general good coherence and eddy distribution. And at 1,000 meters, we can see the signature of the eddies at depth. And we can spot also the Mediterranean overflow water that are salty and warm on this side. And this is associated with the confidence interval. The main result here is that the confidence interval is worse between the shelf and the Gulf Stream, the jets, at the surface. And for the deeper region at 1,000 meters here, it's really in the jets that there will be the worst confidence interval, which coincide with the regions where there is the largest variability of temperature and salinity. So that's where the models are less in agreement, our 15 models. And so, yeah, this is a signature of that. We did something cool also with this model. We try to find what is the relative importance of the inputs for each output. So we use the game theoretic approach that is called SHAP, SHAP. Maybe you know about it. And it is a Python library that is using different type of method to compute a single value that is called the relative importance. That's an easy one to understand. And I won't enter into detail on how they do that, but because there's different ways. But I summarize that with these two plots. So the first one is for each input, you have the relative importance in percentage for learning the output. So the main result is that the SST is the best predictor for all of our output, temperature, salinity, and mixed layer depth. Then is the mean dynamic topography, and then it's latitude, longitude, the day of the year, and the sea level anomaly. And then there is all of those small ones, which are bathymetry and the UNV, and the anomalies, which are small on average, but for specific profiles, they can be large. So we still keep them in the analysis. And against depth, it was interesting to see that the sea surface temperature will explain very well, but will be very important. Almost more than 50% is explained by SST for temperature, which makes sense because it's supposed to be the same value. So the network learned that. But when we go deeper, it decreases sharply, and that's the mean dynamic topography that is the main descriptor. So the mean dynamic topography give actually a good first guess of the temperature and salinity profiles. Okay. That's the last slide I wanted to talk about. We can use OSNet to explore theoretical inputs. So here, to illustrate that, I took an example. So I took one day, 2006, where there is two large eddies. It's actually one warm meander of the Gulf Stream and a cold eddy that is lost in the south. And so I take a section from 42 to 35, and I do the prediction with the surface data. So this is the prediction here, temperature and salinity. There is this W shape with the cold eddy, cold and fresh, and the warm and salty here. And then I do the same prediction, but I'm changing the input of sea level anomaly. I put it to 0, just flat. And so what the result is, it looks like the mean structure of the Gulf Stream without eddies. There is no disruption anymore. And there's just isopycnal that are sloping, right? And like I compute the anomaly between these two. And so I see exactly what is the effect of the sea level anomaly on the interior of the ocean. Or we can see the other way. We have here a tool to study how the interior of the ocean's behavior reflects on the surface data. Right. And so we are exploring that with Guillaume now and trying to find use for that, but it's very easy to manipulate and very fast to compute these predictions and to test different inputs and see how the temperature and salinity profile will change. Okay, so to conclude, I will repeat myself a bit, but we train a neural network to predict TS profile from the satellite data. And the output is we generalize that on a daily quarter-of-a-degree grid that we call the OSNet for Ocean Stratification Network. And this product is distributed on Zenodo, so it's a daily map of this region. You can type OSNet on Zenodo and find it. It's particular because in this product we try to respect well the upper ocean stratification. So we don't have any density inversion, and we have an accurate mixed layer depth estimation. And it's an observation-based daily product of the ocean, which is high resolution. For the future improvements of the model, right now we are working on two different things. The first one is that we are trying to include the profiles of different lengths in the learning, because right now we only have profiles that will reach 1,000 meters. So to do that, we just added a layer in the network that will multiply the output by a mask that is 0 when you have not a number and 1 when you have data. And hence the prediction in the loss is transparent when you don't have data, and it works. You can get shorter profile in the input. So I tested that, and it's working well. And so that allows to predict over the shelf, and that predict also deeper. We can put profiles deeper and go to 4,000, 5,000 meters. And the second thing we want to test, and we are testing right now, is to take patches of satellite data as input instead of a single point for each profile. So we think it's quite important to have the surrounding, the surface for each profile, especially in a frontal region like that. So the network could learn if he's on the verge of on the border of an eddy or of a front, or near a coastline, etc. And this is still in development. And finally, the models and the code are available on GitHub. Guillaume put that in a friendly, user-friendly package. And so I encourage you to try it and use it. You can do your own prediction with your data for this region only. And you can play with the models. Yeah, thank you.